Hi everyone, in this lecture we'll talk about how you can find the time complexity of recursive algorithms. Okay, so let us discuss that as well. What happens in case of a recursion is, what we will do is we will adopt a very simple formula. The formula is the total work done is exactly equal to number of calls, the total number of recursive calls into work in each call. Okay, so let me try to explain you with the help of few examples, and then it will become more clear. So let us see this power function. It is written recursively, so it is computing a raised to the power n. So f of a comma n is written as a into f of a comma n minus 1. Okay, so how many calls we are going to make? So it is very clear that for n, let's say we are computing 5, a raised to the power 5, so it will make a call to a raised to the power 4, a raised to the power 3, a raised to the power 2, a raised to the power 1, and a raised to the power 0. So it is going to fill up the call stack, and the space it will take, it is going to be order of n, and also the time it will take, it would be nothing but order of n, because the number of calls is n, and in each call we are doing this work. This is multiplication and this is a constant work. So the total work done is k into n. Okay, where n is the number of calls and this is the work in each call. So hence we can say it is going to be order of n. Now there may be multiple ways or multiple algorithms to compute this. Now someone may write this kind of a recursive function, although it may appear it is doing something like log n or something like that, but let us try to analyze carefully. So here what it did, it did a raised to the power n is written as a raised to the power n by 2 into a raised to the power n by 2. Okay, so we are making two function calls, f of a comma n by 2 multiplied by f of a comma n by 2. Okay, so when you talk about time, the time will get added, time will not get multiplied. Okay, but the answer will get multiplied. So what we are doing is, if this is odd, for example we are computing 2 raised to the power 5, then it is written as 2 multiplied by 2 square into 2 raised 2 square. Or if we are computing 2 raised to the power 6, for even numbers we are computing, what is half power square? This term is half power square. And if n is odd, we are multiplying with a, so we are multiplying with a. And if n is even, we are simply saying it is 2 raised to the power 3 into 2 raised to the power 3. This is what half square is. So this is the formula that we are using. This is when n is even, and if n is odd, we are again multiplying it with another a. Okay, now the multiplications take linear time, but the time will depend upon these function calls. So how many function calls we are going to make? So let us see. So we have let me try to show it to you. So we have n. So from n we are making two calls, one to n by 2, another to n by 2. Then from here we are making two calls, n by 4, n by 4, n by 4, n by 4. Okay, and this will go on until we reach a level where we just have one call, something like this. So what you can observe is the total number of function calls. We have one function call on the first level, we have two function calls on the next level, we have four function calls on the next level. And how many levels we will have? We are going from n to 1. Every time we are going to reduce by a factor of 2. So the height of this tree is going to be log of n. Okay, the last level would have how many nodes? The last level would have 2 raised to the power log of n nodes. Okay, this is what it is going to be. So yes, 2 raised to the power height, where height is equal to log of n. Okay, where height is equal to log of n. This is the number of nodes we will have at the last level. Now you can see this forms a geometric progression. It's a GP, and the sum of terms of a GP is nothing but 2 raised to the power n minus 1, where we have number of terms. The number of levels is also log n. Okay, so I can say it is nothing but 2 raised to the power log of n minus 1 upon 2 minus 1. So now what this term it is going to be, it is nothing but 2 raised to the power log of n to the base 2. So this is nothing but this is equal to order of n. Okay, so that means this code is still order of n. It is not log of n, it is not n square, it is still order of n. So effectively speaking, the total work that we are doing in the two examples, power function 2 and power function 1, this is exactly same. Then what we are doing extra here? Okay, so what we are computing extra is we are actually making this function call. It is not needed. Okay, what you can do instead of doing this function call is you can square the result that is received from this call, and you can avoid another function call, because this call and this call are going to return the same result. So instead of making these calls, what I can do is I can reuse the same result and do the multiplication. That will help me to reduce time. So let me also talk about the space complexity of this method. Then when you talk about recursive programs, the space would be the time taken by the maximum depth of the tree. Okay, so if you make a recursion tree, then the space would depend upon what is the maximum depth of a branch. Okay, max depth, because at any point in the call stack you're going to have only one branch that is going to be there in the call stack, and in each node what is the space that you have taken. Okay, so space is nothing but maximum depth of the branch into memory consumed by one node. Okay, memory in each call. So in each call we are using a constant memory, so in this case it is order 1. The maximum depth is order of log of n. This code has a space complexity of order of log of n, and it has a time complexity of order of n. Okay, this is about space and this is about time. The first code that we have seen, it has both the space and the time as order of n, because call stack is going from n, n minus 1, n minus 2 up to 1. So the call step is n level steep. So both space and time are going to be order of 1 in this case. Now let us look at another example, that is power function 3. Here we are doing some smart work. We are computing what is a raised to the power n. It can be written in terms of a raised to the power n by 2, and we are checking if it is we are squaring this up, and we are checking if it is odd, then we are multiplying it with a, otherwise we are not. So all of this is a constant work. The only thing we are doing is we are reducing t of n into some constant work k plus t of n by 2. Now it is very easy to solve. We can say t of n by 2 is nothing but k plus t of n by 4. So this goes on. Finally we have t of 1, then k plus something something. So effectively everything will cancel up, and you will get t of n as summation of k. How many times? Every time you're reducing by a factor of 2, it would be k into log of n. Okay, so it is order of log of n. That means the number of calls that we are making is order of log of n. Okay, and the space complexity is also order of log of n because of the depth of the call stack. Okay, so let us say if I compute 2 raised to the power 16, I make a call to 2 raised to the power 8, I make a call to 2 raised to the power 4, 2 square, and 2 raised to the power 1. So we have roughly, it's a linear tree. It's not going to make two calls. So we have order of log n both for the space and for the time. Okay, n by 2, n by 4, and so on. So this goes like this. So I hope this method is best if you want to compute a raised to the power n. Then definitely this is the most efficient out of all the three methods that we have discussed. So I hope now this is clear to you, and that's all for this lecture.